For this video, I wanted to show a summary of the equations that we've introduced for this chapter, and then go through sample calculations of the last two equations that we've introduced but haven't yet practiced. On this equation summary slide, I wanted to clarify two things. One, which equations are not on your equation sheet, and then to clarify how you're determining the number of sig figs to report in a final answer. The order that I have our equations here is the order that we've introduced them. So remember, our very first equation in this chapter was calculating the enthalpy of reaction using our products minus reactants. I'm highlighting this one because it is not on your equation sheet. For this equation, you will use decimal places to report your final answer. So the decimal places that you have in your enthalpy of formation values will determine decimal places in your final answer. The same applies for equation number 2, also highlighting this one because it is not on your equation sheet. Same setup and same rules for decimal places. The third equation that we have in here is our Gibbs free energy equation. Our delta G naught equals enthalpy minus temperature times entropy. On your equation sheet, I believe this is written in standard form. Sorry, I don't actually have it in front of me right now. But realize that this equation could be used for standard or non-standard notation. So either one applies. We only put one version on your equation sheet. From our Gibbs free energy equation from number 3, we then derived an equation to calculate the temperature at which a reaction will change spontaneity or the temperature for a phase change. I'm highlighting this one because it is also not on your equation sheet. I forgot to specify on that one for temperature. This one, because you're using division here, you would use sig figs to report your final answer. Equation number 4 was again the same setup as equations 1 and 2, setting up products minus reactants using free energy of formation values, again using decimal places to report final answers. And then the last two equations, numbers 5 and 6, that we just introduced on the previous video, relating non-standard delta G to our standard delta G value. And double checking this one, I believe I have another typo in here. I apologize for that. This should be plus RT ln of Q. I apologize for that. For equation number 6, that was derived from number 5, identifying what happens at equilibrium and giving us a relationship between standard delta G and our equilibrium constant. So equations 3, 5, and 6 are on your equation sheet, the rest are not. And so I wanted to go through a practice calculation using the equations we have not used yet. In this question, we are given delta G naught for the dissociation of acetic acid. So here we have the dissociation equation. Should look familiar, it's just an acid reaction. We are given a value of 27.1 kilojoules per mole, and realize that it's implied, sorry about that, it's implied to be a positive value, even though the positive is not written in here. So pluses don't have to be written with values, by the way. And we're asked to calculate our equilibrium constant. For this calculation, we will be using equation number 6, where we have delta G naught equals negative RT ln of K. To solve this one, I like to actually manipulate my equation to solve for the ln of K. And remember here, we're specifically referring to Ka, but the subscript doesn't matter. And manipulate my equation to solve for that. Now again, the common mistake I see students make is omitting that negative sign carried over with the RT. So using that equation, plugging in all of the values that we are given, We have our delta G naught value on top, again, recognizing that's in kilojoules per mole. Starting with my negative sign, when I plug in my R value, because we're using units of energy and joules, we want to use our value of 8.314. But again, recognize that that's in joules. So I'm going to convert my R value into kilojoules. And then plugging in my temperature. So notice temperature is not given in this problem, but because we are given standard Gibbs free energy, the temperature is implied to be standard temperature. I'm going to use the optional 0.15. And I've lost my calculator. Give me 1 second. Okay, so I'm going to use the optional 0.15 in my temperature conversion. When we plug all of this in, we get a value of negative 10.9326. Keeping extra digits here because this is not my final answer. Realize at this point I've solved for the natural log of K. If I want to solve for K itself, I need to get rid of my natural log function. I'm going to raise both sides to the E, and therefore my K value is going to be, we're using sig figs in this equation because we did primarily multiplication and division. So 1.79 times 10 to the negative 5. To check that our answer makes sense, realize that we have a positive value for delta G naught. Positive value for delta G means that we have a reactant-favored system at equilibrium. A reactant-favored system indicates that we should have a small K value, and that is in fact what we've solved for here. For our next calculation, we are going to use the same system, same delta G naught information, but now we want to know, is this reaction spontaneous at a given temperature given these concentrations? Remember that if we're asked to determine spontaneity, we're using non-standard delta G. And so that, of course, means that we need to use our equation number 5. In this equation, we, of course, are given delta G naught. R is a constant. T we need to convert to Kelvin, and Q we need to calculate. So I'm going to do my setup for Q first, and hopefully not run out of room. So again, we have products over reactants. Plugging in our values, we have paying attention to each substance and their concentrations. Acetate is 0.045, hydronium is 0.025, and acetic acid is 1.15. Everything has a coefficient of 1, so we don't have any exponents to worry about in here. Do remember that at this point we can use any type of reaction, and so pay attention to your coefficients. Make sure you include them as exponents in your setup for Q if you need to. Our Q value with extra digits is 9.7826 times 10 to the negative 4. I'm also going to do my temperature calculation here. We're given 95 degrees Celsius, adding our 273.15. We get a 368.15 Kelvin. Setting everything up for our equation. Plugging in our delta G naught value. Adding to this the product of all of our RT, ln, and Q. Again, converting my R into kilojoules per mole per Kelvin times temperature times the ln of our Q value. For this calculation, the easiest thing to do for the setup, I think, is to actually plug everything in backwards. So I actually like to take the ln of my Q, keep this number in my calculator. So do this one first, then multiply by my R and T. And then add everything to my delta G naught. That way I don't have to retype anything in. I can keep all of the numbers in my calculator. And remember, for this calculation, because our last step is addition, we're going to go by decimal places. So I have 1 decimal place in delta G naught. That means that I'm going to round my final answer to 5.9. In here we have kilojoules per mole as our final answer. So realize the question was, is this reaction spontaneous? And just answering yes or no will get you 0 credit for these. We have to go through the calculation and remind ourselves that because this is a positive value, this indicates that under these conditions of concentrations, this reaction is non-spontaneous. In other words, this reaction needs to go in the reverse direction to reach equilibrium. One quick note on units. In this chapter, there are some cases where you will calculate delta G naught first from other data. And in some cases, that per mole quantity might not exist. But realize, of course, that it does exist in our R value. So there will be some cases when per mole doesn't necessarily match up and won't either cancel out or be the same. For this chapter, it's okay. Report your final answers in kilojoules or kilojoules per mole. So this per mole part is optional for units. And at this point, you are ready to work on group quiz number 20. So 2 things here. You are using the same system for both questions. In one of them, you're asked to determine if it's product or reactant favored. And in the second one, you're asked to determine if it's spontaneous or non-spontaneous. So make sure you answer that question, justify it with your calculations.